loud. Okay, okay. So I originally planned to do this for you guys at the next telecon, but I figured I'd do it for you guys now since we had a sudden change in speaker. Let me make sure I have the right. Uh, yes. Okay. Perfect. Always show. Okie dokie. So yes, I originally planned to do this for you guys at the next monthly meeting at the end of this month, most likely the beginning of January due to the holidays. Um, but due to the change of speaker, I'm going to do it for you guys now. And so it's to go over the previous list of transients that could feature in the stream for Kilonova-Catcher in the future, or is just some other type of transients that multi-messenger astronomers find interesting. A few of these you guys will recognize, like Type 1a supernova, but others you guys may be less familiar with. And so, why expand beyond Kilonova? So, we really want to maximize our science return from the Kilonova infrastructure and amateur network. We want to keep you guys engaged between gravitational wave events. This is also a really, really good way to validate pipelines and calibration with a diverse array of targets. It provide new opportunities for not only you guys to learn, but for the brokers and other systems that we're developing. It's really good feedback to see how an array of diverse targets will um, develop. And this will help build institutional knowledge, like I just said, for rapid response observing, and it's great discovery potential for genuinely new phenomena. And so Kilonova-Catcher is unique. We have fast follow-up capability, and we can utilize it strategically while maintaining Kilonova readiness and be able to expand our understanding of what a citizen science network is really capable of. And so, kind of as an operations recap for Kilonova, we trigger on LIGO and Virgo alerts. We have sky map tiling, multi-night campaigns. We observe every 6 to 12 hours for several days. Um, we have early detection goals, color evolution, characterization, and then something very similar for GRB afterglows. We respond to swift and Fermi alerts. We really go for minutes after we understand what's going on. Our cadence is very quick, and we're looking to understand jet physics, late time kilonova searches from short GRBs. And so we have an overall a median aperture of about a foot or 12 inches. We use a variety of filters, and we get a pretty good depth from 18 to 21 magnitudes. And we have our strengths. We have this rapid response. You guys are really communicative. You have great technical expertise. You guys can do sustained monitoring. You have geographic coverage. And this ability to really, and this, I'll go back to it again, this rapid response. And, there's a lot of bureaucracy and red tape that really puts a stopper in a lot of multi-messenger and fast transient physics observing in astronomy that you guys aren't really bound to. You guys have your backyard telescopes, you guys have community telescopes that you can just respond with. And it really creates this unique environment of there's great opportunity here. And so what makes a good Kilonova-Catcher target? So beyond Kilonova, so we have fast evolution, so significant changes on hours to day timescales, early time critical, so getting those first hours or days is very scientifically valuable. You have multi-messenger potential, so you coordinate with X-ray, radio, neutrino facilities, amateur accessible, so magnitude range is suitable for network capabilities, and then a high scientific impact. So we were addressing open questions on clear physics. And so we can leverage our strengths, rapid response, distributed network, photometric expertise to really kind of get a hold of these unique open questions that we see in nuclear astrophysics. So to kind of go back for a moment, and so I have this figure up here, and I don't know if any of you have seen this before. I'm sure Michael has, but this is a model of a kilonova associated with a neutron star merger. And it's showing the fast effects of the evolution in blue and slower effects in red. And then the associated graph that shows how the model matches with the data from the observed kilonova. And so we're seeing how continued observations of these objects, and maybe at one point when we hadn't identified them as kilonova, is crucial. So this, early time observation is crucial to understanding its evolution overall and what's really going on with the physics. So beyond kilonova, what else is transient? What else evolves at these timescales that would interest or would benefit from our unique skill set here within Kilonova-Catcher? And so during November's monthly telecon, I talked about jetted tidal disruption events. And so what are these events? And so tidal disruption events occur when a star passes too close to a supermassive black hole and is torn apart by these extreme tidal forces, a process sometimes called spaghettification. So as the star is ripped apart, a stream of stellar debris falls backwards towards the black hole, forming an accretion disk. And so this process releases a tremendous amount of energy across the EM spectrum, and it creates a transient brightening that can last months to years. And so jetted tidal disruption events are a rare subclass of all TDEs. So that means when there's a jet, a beam coming out of the event. So as the star is ripped apart into the black hole, there's a jet that comes out. And so only 1 to 10% of all tidal disruption events have it's where the accretion process launches a relativistic jet. So a narrow beam of plasma that's moving at a significant fraction of the speed of light. And these jets produce non-thermal emission across multiple wavelengths, particularly bright in X-ray and radio. And so the key characteristics of jetted TDEs, they have this rapid optical brightening over days to weeks, much faster than a typical active galactic nuclei variability. They have blue thermal continuum from the hot accretion disk. They have non-thermal emission from the relativistic jet, so X-ray radio, they get energized enough. They have multi-wavelength evolution, so this requires coordinated observations, much like we do now. And it's a rare occurrence. Only a small fraction of TDEs produce jets, which means you have only a few opportunities to study them from the overall population. And so a TDE observing strategy, what would it look like? Well, it looks very similar to what we're doing now with GRBs and Kilonova. And so we have, this Wiki Transient facility, which is utilized for discovery. Its role is initial optical detection and rapid classification. For jetted TDEs, we're looking for that rapid optical brightening in galactic nuclei. ZTF would trigger follow-up before peak brightness. We have looking for a nuclear location, which would flag potential TDEs. We have blue colors and smooth light curves that would distinguish it from a regular supernova. And ZTF would provide discovery coordinates for SWIFT and other multi-wavelength follow-up. We have several different examples from 2020 and 2022 the papers were in where we've really understood the evolution of these jetted TDEs. We also have SWIFT observatory. So SWIFT can do X-ray characterization. SWIFT is really, really good at this rapid X-ray follow-up and jet identification that other observatories around the world cannot do. Other X-ray observatories would take days to do a targeted opportunity. SWIFT can do it, within an hour. And we also have the burst alert telescope. So we have the all sky gamma ray monitor. We have XRT, UVOT on SWIFT it would really, really, help coordinate these events. And so much like we have the similar infrastructure and support for GRBs, we would have it for TDEs as well. And so the next topic of discussion would be type 1a supernova. And so I'm sure many of us are familiar with, I'm sure many of us are familiar with type 1a supernovas. Kilonova-Catcher did do a paper on this. They did observe this, SN 2023 WRK. And just as a reminder for the science, type 1a supernova are thermonuclear explosions of white dwarf stars in binary systems. So they are amongst the most luminous stellar explosions in the universe, briefly outshining entire galaxies and reaching absolute magnitudes of, -19. And so despite being extensively studied and often used as cosmological standard candles, fundamental questions about their progenitor systems and explosion mechanisms remains unsolved. Even within our own observations of SN 2023 WRK, we are unsure about why there was so much leftover silicon and nickel in the system. And so, the basic physics of white dwarf type 1a supernova is that there's a carbon oxygen white dwarf that approaches the Sanders-Sarkar limit. It's pulling mass from another object. It's a thermonuclear runaway, so carbon fusion ignites. We have these burning timescales that are, much smaller than the overall dynamical timescale, and it causes this, complete disruption. So there's no remnant left behind, unlike in other core collapse supernova, which is there's not enough external energy to compensate for the mass that's already there. And so understanding these objects is really, really important. And so the Kilonova-Catcher niche is, to bridge this gap between discovery and major facility follow-up. And so it's really, really important that we capture these, shock breakout signatures, the, NI disruption, ejecta mixing, and so that's where Kilonova-Catcher came in. And Kilonova-Catcher, was like 30% of our observations for SN 2023 WRK. So we're already seeing in really clear ways, a publication, how important Kilonova-Catcher is, all right, for type 1a supernova. And type 1a supernova is, a sister question to, hey, what happens in these high density environments like with kilonova? Well, white dwarfs are the, third most dense objects in the universe, and understanding, how these events occur, will contribute overall to these open science questions. Can you guys hear the video or no? Can I get a thumbs up from somebody if you can hear the video? Okay, you can hear the video. Perfect. Okay, can't. Eric says can't hear it. Me be able to share computer sound. All right, that should work now.
Uses something called a standard candle. A standard candle is a type of object or event that emits a specific known amount of light, allowing scientists to find its distance with a straightforward formula. This works because light sources appeared predictably dimmer the farther they are from an observer. Since astronomers know how much light a standard candle gives off, they can determine its distance by measuring how dim it appears from Earth. Since only very bright objects or events are visible in the far reaches of the universe, the options for standard candles are limited. Some of the best and most reliable are exploding stars, called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. Some of the time, it may be a white dwarf and a larger host star. Scientists think the white dwarf steadily accumulates material shed by the host star, gaining mass in the process. When it reaches a specific tipping point, the white dwarf has gained enough mass to trigger a runaway reaction at its core, and it explodes spectacularly, sending out an expanding sphere of super-hot material that glows from the energy of the explosion. In other cases, scientists think two white dwarf stars may form the binary. Either the stars finally merging together triggers the supernova, or it happens as they spiral in closer and closer, while the more massive of the two pulls material off its companion in the final few minutes. Before they merge, it reaches the same mass tipping point and goes supernova, always releasing a similar amount of energy. Because white dwarf explosions are all so similar, the energy and light output of type 1a supernovae are easy to standardize. Type 1a supernovae are rare in any one galaxy.
All right, so now we have this understanding of, you know, or a re-understanding of what type 1a supernova are and what the progenitor question really is. And so it's, do we have the single or double degenerate scenario? And so, these early time observations matter because we have this initial flash when shock reaches surface. We have the 56 nickel distribution, so early light curve shape depends on the radioactive material location. And then we have the companion interaction, so ejecta colliding with the companion star, and what happens then? And so we have the rise shape, so the power law versus exponential depends on progenitor radius and the explosion energy. We have color evolution, so temperature evolution constrains, ejecta composition. And then early specter, carbon, oxygen, silicon features reveals burning front physics. So what is going on at the forefront? And so the problem is that most supernova type 1a are discovered days to week after explosion, which misses critical early phases. And this is where the role of multi-facility observations come in. And so I'm sure I don't need to tell you guys this, but you were there for this one at least. All right, that the earlier we can get it, the better we can have our models, the more we can really take from these unique and pretty rare events. Um, Not too rare, but 2,000 about 3,000 type 1a supernova discovered by CTF per year is what I believe. But only about 50 to 100 are caught within 3 days of explosion. And only about 500 to 800 are caught before maximum light. And so if we were to continue to observe type 1a supernova, especially as the LSST releases alerts, it would really need to constrain um, which ones are significant, which ones are within Kilonova-Catcher's ability to observe. But because there's so many that are observed a year, we could really have a steady stream of them to contribute to and to then continue to contribute to the community with. All right. So on to our second to last event. So luminous fast blue object types, or optical transients. Uh, these are these are interesting in the sense that the physical origin is quite unclear. So, luminous fast blue optical transients are a newly recognized class of extremely energetic stellar explosions. And their properties really challenge, existing astrophysical models. And so we have a prototype, AT 2018 COW, I believe, um, that reached peak luminosities of like 10 to the 44 erg per second, so about 100 times more luminous than typical supernova. And these evolve on timescales of days rather than weeks. And so these transients are then characterized by one, extremely rapid rise times of 2 to 4 days, very blue colors indicating extreme temperatures, all right, fast fading after peak, and this strong X-ray and radio emission correlation suggesting that we have an interaction with pretty dense circumstellar material, or there's a central engine activity. And so only about a dozen LF bots have been discovered to date, making them among the rarest transient phenomena known. And so we are still very, very much uncertain about the physical origins of LF bots. And so there's been a few proposed mechanisms. So tidal disruption of stars by intermediate mass black holes. That's about 1,000 solar masses. Feel free to correct me if somebody knows better. They could be failed supernova, where fallback forms a rapidly accreting black hole or a magnetar. These could be exotic stellar explosions with unusual energy sources. These could be interaction powered events. There's a lot of potential sources or progenitors of these LF bots. And therefore, multi-wavelength observations are quite critical. We want to see them in X-ray, we want to get them in radio, and to really just have this data reveal what would be the ongoing central engine activity and what the circumstellar interaction is. And that would be X-ray and radio. Optical and UV would track the thermal emission from these events. And so the extreme rarity, the fast evolution of LF bots, just like Kilonova, make them exceptionally challenging to study. And just like with Kilonova, missing the first few days means missing peak and crucial constraints on the explosion mechanism. What is Kilonova-Catcher really good at? Really fast responses. And to continue to contribute to these relatively unknown progenitor systems, all right, would be a great way for us to contribute to the community, to keep getting our name out there, for you guys to be on papers, and to continue to get funding in all practicality. And so speed is absolutely critical for LF bots. Like I said, speed is essential. Here is a picture from, I believe this was Hubble, that took one of the first images of a LF bot that we've ever captured. You see a galaxy here, and then you can see this star, or this transient event, just absolutely booming in brightness compared to these, otherwise softer, either nebula or smaller galaxies around it. So we have blue transit. So alert criteria would be like blue transients with greater than 1 magnitude per day rise, no clear host association. We're looking at pretty low absolute magnitudes. And so you would have to coordinate immediately with major facilities and really get some response understanding from them. And so ZTF's alerts would be great companion pieces for this, as well as to see if other observatories would be observing these. All right. And then we have this like kind of a far off, maybe on occasion, if the criteria is good, active galactic nuclei. So these aren't necessarily like transients we would be observing constantly, or that you guys would be like, hey, you have AGNs every so often here. This is more like if the opportunity presents itself, if there's nothing else to do, if you guys are interested. So most active galactic nuclei move too slow. All right, they're not necessarily transients, but some are worth watching. And so typical AGN, so what are AGN. So, and why most don't fit for Kilonova-Catcher. So this is like the selective case. So active galactic nuclei are powered by accretion onto supermassive black holes at galaxy centers. So these are supermassive black holes that are 10 to the 6 10 to 10 to the 10 solar masses. That's 10 times the size of the sun at galactic centers. And so while AGNs are intrinsically variable across all wavelengths, most exhibit variability on timescales from months to years. So far too slow for KNC's rapid response capabilities to really be utilized, right? Other observatories, other systems can observe them. That's not really our thing, right? And so typical AGN monitoring requires baseline observations over months to years to characterize long-term trends, making them unsuitable for fast transient focus of the Kilonova-Catcher network. Additionally, most AGN are persistent sources, so always on, rather than true transients. And their science questions usually require long-term monitoring campaigns, and that extends beyond KNC's mission scope. However, there are the occasion where there is a rapid state change AGN. What does this mean? So a small subset of active galactic nuclei will exhibit dramatic changes on weeks to month timescales that could benefit from KNC monitoring if there aren't designated observatories already doing so. And so changing look AGNs transition between type 1, these broad emission lines, and type 2, no broad line states in weeks to months. And this is possibly due to dramatic accretion rate changes or variable obscuration. There's something called that I learned when developing this presentation called quasi-periodic eruptions. These are X-ray flares that repeat every few hours from AGN, and they potentially could indicate the orbital motion of material around intermediate mass black holes, which is really cool. And so these are extreme nuclear transients as well. And so extreme nuclear transients from DTF's Nuclear Transient Survey show rapid AGN brightening that may represent partial tidal disruptions or accretion rate changes. So for these targets, KNC role would be optical photometry to track state changes, coordinate with Swift NICER for X-ray timing, monitor color and spectral evolution during transitions, especially if there's nobody else monitoring, or we are aware that, okay, maybe somebody else is doing something. Like this could just be unique opportunities. Like if the transition state is exceptional, there's these quasi-periodic eruptions going on, there's other mechanisms that are making this interesting. This could be available to you guys, but mostly we'd be focusing on LF bots and good question, Eric. But usually you guys would be focusing on jetted TDEs, possibly focusing on jetted TDEs or type 1a supernova or LF bots. Um, so so this isn't something like, oh, Kilonova is changing its focus or you guys will be doing more of these. It's more like we're going to be possibly exposing you guys to the opportunities to follow up on other transient events at your leisure, with priorities being on Kilonova and GRB afterglows. Here's a really cool demonstration of an active galactic nuclei. I found just quite interesting. I think NASA always does a good job with its examples. And so Eric Browens asks the question, how soon after, oh, I touched my screen the wrong way. So how soon after detection could the LSST detect a, why is it disappearing? So how soon after discovery of the transient is it known to be of type LF bot? Um, that's a good question. I believe I would have to give you a more pedantic answer afterwards. Like I can look it up, but I believe because of how bright and how blue these things are, it is quite quick. You can determine that it's an LF bot because these are scales, hundreds of times brighter than any other supernova. Um, but the issue is catching enough of the early photometry to be able to really say, yeah, this is an LF bot. Um, and so that's where the balance comes in now. So much like Kilonova, it's been a matter of like serendipitous luck that we capture enough of the initial events. But the non-comparatively is that they're so bright and so much brighter than other things, even if they're evolving fast, that you can very quickly kind of be like, oh, hey, and say, yeah, this is an LF ball, let's observe. Let me go to the next slide. And so, like I mentioned before, there's going to be a lot of cross-cutting benefits. So beyond individual targets, we'll be able to test photometry, calibration, extinction corrections with diverse colors and evolution timescales. We're able to keep you guys active, trained, invested between gravitational wave events. And also prepare you guys for the nuance that may come during, '05 or when Lisa comes aboard or when the LSST. Can you guys be able to, let's say I am asleep and Damiana isn't responding, or vice versa, or Damiana isn't awake yet and I'm going to bed. Could you guys then, with this experience, because you'll have more experience responding to transient alerts, be able to respond on your own time? And so this will help you guys build experience with fast evolving transients to prepare for Kilonova discoveries. And also be able to operate, let's say Damian is coordinating and I are coordinating a larger scale observation campaign. Can you guys independently respond to unique events, and without our individual guidance at all times? And so as Kilonova-Catcher is going to evolve, there will be gaps, and we're like, okay, in personnel, so to speak. So we'll have an increase in detection alerts, but we'll still have, maybe just myself and Damien, another scientist. And can you guys be able to really facilitate yourselves and others in between periods of really all of us getting on a Zoom together or chatting together? And so this will really help that. And so we'll also be able to benefit from collaborative relationships, so establish connections with discovery surveys, major facilities. And there's so much discovery potential here at the dawn of the LSST and a lot of these, this reinvigoration of multi-messenger astronomy. And so we are now positioned to catch genuinely new phenomena in early phases. And we're kind of honing in on a, underutilized aspect of multi-messenger astronomy, which is the citizen, which is you guys. And so there will be practical considerations as well. So we have to maintain Kilonova readiness. And so, like I said before, this won't be the case of priorities. over Kilonova. So the Kilonova and short GRBs will be the primary mission. There will be a clear prioritization scheme. We will tell you guys, hey, this isn't more important than this. So if this occurs, you guys will know firsthand. That'll be built into the alert stream. We'll use downtime strategically. You guys won't be, forced to do this. This was to fill gaps between GW follow-ups, poor weather nights. Modest cadence is sufficient, so nightly to every few days is adequate for most of these targets. There'll be automated filtering is essential. You guys cannot manually vet every transient alert. That'll be built into these alert brokers. And we'll start small this and scale very carefully. Like obviously you guys are pretty much built into how we progress Kilonova-Catcher forward already. And so you won't be inundated instantly. I'm sure you guys would like to see those numbers, but you guys won't be inundated. And certainly we couldn't handle an inundation ourselves. And so we would pilot with, 5 to 10 high value targets. We would evaluate success, really take your guys' opinions into account for even taking any of these opportunities, any of these types of events. And so the key principle is that this is supplementary science that strengthens, not weakens or distracts from the primary mission capability. And so part of that would be using discovery surveys, filtering services. We would build automated ranking, rise rate, color, spectral class, brightness. What does somebody else have that would help navigate our observations so that you guys aren't observing into the darkness, even though that's what you guys like to do, so to speak. And so highest priority is JETA TDEs and unusual transients. So these are unique early time windows, high value, certain to address open progenitor questions, which would be early time type 1a supernovae, and then very rarely selective participation in AGNs, but only for possible unique rapid state change candidates. So pilot program, develop automated alert filtering, create observing templates for each of the transients classes, and then evaluate. So papers contributed to, network engagement, pipeline performance. And so this would be like a cyclical path of how we would develop these over time. Any questions? Let me pull up the. Alrighty, so do I have any questions from the group? And while somebody asks a question or takes a moment to do so, I can pull up my notes on LF bots and answer Eric's question. Okay, so.
Yes, Cristina, maybe the question is, of course, at the very beginning, the transient could be unclassified, and in fact, we don't know what it is.
Yes.
And so how you solved this, I don't know, this ambiguity? Is it a transient, a valuable transient for these targets?
So this isn't something that Damien and I have discussed with great detail. It's obviously a pretty large question. Let's see. But much like we do now with gamma ray bursts and kilonova, there's usually one aspect of the event that we're confident on that we can say, hey, might be worth observing, and then sometimes we don't detect it, we aren't sure. Sorry, one sec. I hear an echo from myself. I'm trying to correct it. So the fundamental issue for a lot of these is that you need to decide whether to observe within hours, but definitive classification using spectroscopy can take days to weeks. And so this would be a risk stratified response based on photometric properties. And so a lot of these brokers would have automated pre-filtering based on models and machine learning algorithms that have been trained to really try and as accurately as possible determine what these events are. So we set up alert stream filters for each transient class with inclusive criteria. So for TDEs, we have a nuclear location. So less than 2 arc minutes from a galactic center, blue and rising. For GRBs, these are external triggers. So we have Swift and Fermi alerts that tell us, but they do it the same way. Do the initial observations, initial detections match a model that we have? These models are trained on even the non-detections over time. And so that's what a lot of the science that we do with non-detections come from, is that yes, we observe these alerts, they kind of match what we were looking at. We didn't get a lot more, but we can train these machine learning algorithms and implement them into brokers to kind of help us with at least some confidence with some experience to say, hey, is this or is this not this type of event? And so for tidal disruption events, it would be a nuclear location, so less than 2 arc minutes from a galactic center, blue and rising. For type 1a supernova, we're looking inside of a galaxy. We're looking for a moderate rise rate. We're looking for typical supernova colors, but it's just much brighter. For LF bots, this is going to be a very, very fast rise rate. And so, we're seeing something that's not only super, super blue and super bright, but it's also rising really quickly. And so it is within these brokers, within these algorithms, that we'll be able to say, hey, we have, these example events, like we have GW170817 for Kilonova. We have even more events for these other type of phenomena that will tell us and that have contributed to improving our ability to detect them early or characterize them early, identify them early. But full characterization would come much later, unfortunately. And so that's the balance here.
Thank you.
Mhm. And then for LF bots in particular, connecting back to Eric's question, how soon after discovery of the transient is it known to be of type LF bot? ZTF could detect rapid brightening. So initial classification is unknown fast transient or possible LF bot candidates. You'll have this extremely fast rise rate, very, very blue colors, no clear host or offset from the galaxy. Um, multi-wavelength observations would happen in, 2 to 5 days after discovery. And so Swift would detect bright X-rays. The color would remain extremely blue. We would be able to continue be able to see a continued rapid evolution. And then at the 5 to 14 day mark is when we start to have maybe confirmation. We would have spectroscopy. We would have a multi-wavelength behavior be able to confirm it. And so the bottom line to answer your question is the point of Kilonova-Catcher, which is you must respond immediately to fast transient alerts based on photometric properties alone before confirmation. And waiting for spectroscopic confirmation means missing the critical rise phase and critical data. Any other questions?
Yes, do you intend to manage something in coordination with Astro Colibri
It is very
to, to,
possible.
to feed the alerts and to say this is we take this alert in a Kilonova-Catcher network? It could
Uh,
be worth also to
yeah,
distribute the alerts between BH-Tom, Rapace, Kilonova-Catcher, and other. This could be interesting for amateurs to know where to deliver the alerts and the alerts which are managed by a team, by a network.
yeah. This would be more of a question for Damien and Sarah with how these alerts would be distributed, how they would be cross collaborated between citizen science networks. Um, I know that um, a lot of the broker systems that Michael develops are all open source deliverables, so anybody could utilize them. But How they're implemented is up to the individual citizen science projects. So it would be something I would bring up to Damien, Michael, and Sarah at one point or another of how we could create maybe a cross collaboration opportunities between not only professional observatories and citizen science networks, but the citizen science networks themselves. And especially at the dawn of LSST when we're just having all of these um, events to go after. Yes, Eric, we would have to go after it based on the rise time and color info. Exactly. Any other questions? I hope everybody's looking forward to the holiday season. I imagine that not much observation is being done with the snow and cold weather about. Um, Minnesota got a few feet dumped on us last week, and then it dropped to negative 14 degrees on Saturday night when I went to go see the Geminids. Um, did anybody get outside to go see the Geminids?
Yes, there is some French amateurs. They succeed in getting impact on the moon.
Really?
Yes, really.
Amazing. Do you have the article or pictures from that?
Yes, I may show you maybe the video if you want.
Yeah, that would be lovely.
This
No,
is it's Jean-François Gou who succeeded in getting the alert. Um, because I am able to show you where is he?
yes, it says
It
all
was
participants.
nice.
Yes, you should be able to share now.
Get it? It's a nice transient.
Yes,
Uh,
I went up about 2 hours north of here to a state forest that was very, very dark. It was a class two dark sky area. And the individual I was with was a little bit apprehensive to be out there. And I'll talk more about this at the monthly meeting. But he was a little apprehensive to be out there. He'd never done something like this before. And he's like, maybe we should move off the road just in case somebody comes by so we don't have to drive backwards. I'm like, no, it should be okay to be on the road. It's safer here on the road. He insisted. I was like, okay. And then I got stuck in the snow. We went into about a 2 foot deep culvert, and I was resting on the frame of my car, and we had to call a tow truck. But we got to wait and watch the Geminids. It was super super clear that night. I mean, just not a cloud in the sky. Low atmospheric density. It was great. I mean, we could see the sparks coming off of the meteorites, and we could see the color, the green color on the back end of it. Just an absolutely phenomenal experience.
Excuse me. It was on Sunday morning. Uh, um, oh, yes, I remember. Um, yes, here it is. I don't know if I may share my screen.
Yes, you can.
So it's a video recorded by Jean-François Gou. It was a bit on the night between Saturday and last Saturday. And here is the video. So you see the moon, the dark side of the moon.
Mm-hmm.
And so maybe you are able to notice here a Geminid impact on the moon.
That is so cool. Oh, wow.
So it's a collaboration managed by an Italian guy in Milano, and they are preparing with the European Space Agency a CubeSat, which will be launched in 2 years and in 2028. And the purpose is to put this CubeSat on the backside on the moon to be able to monitor also both sides of the moon. So with a matter from the Earth and with this CubeSat from the looking, monitoring the other side of the moon and to be able to count all the impact between during meteor showers. So Geminid is a nice event, Leonids. So it's another kind of transient event closer than your kilonova.
That is super cool. I have never seen that. I hadn't even thought about the fact that they would impact the moon, but well, thank you for sharing that. Yeah, it cleared during night of 14:15 or 1 a.m. Yeah. Wow. That's amazing. Oh, wow. That is phenomenal. What a picture. Uh, how many of us here, I'll send a wider email out about this. Let me take a note down. Got images of the Geminids. That was what a cool picture. Amazing. Yeah, we were out there from like 12 to 4 in the morning, and then even on the way back from like 4 to 5 in the mornings. This is Central Standard Time. It was pretty active still. Absolutely wonderful. All right, guys. I think I'll send an email out asking everybody to kind of, include if they've had any of the experiences with the Geminids or any other meteor showers in previous years. And then I will send out an email about, when the monthly telecon will be because of the holidays this year. I think I'll hold it still. That way I can see everybody. But yeah, other than that, thank you guys so much for coming today for the webinar. I hope you found them informative and a little bit more studying after our discussions about, possibly increasing the type of events we see here at Kilonova-Catcher. And then next month, the webinar will be for the month for exoplanets and Lisa. So, if there's any more questions, other than that, thank you guys very much and happy holidays.